Hello. Hello, people. I'm okay. We're about to start. Let me just and mhm. So today we are going to talk about electricity, and let's start. A very nice app that I like to use for electricity is FET, of course. So FET circuits, circuit construction kit, and we talk about direct current. And let's just play around with it a little. And if you have a battery, you have a resistor, and connect to a wire. This is a series circuit. So you can see that the battery produces a voltage. So what a voltage is? Well, a voltage is simply giving electrons energy. So the battery gives you energy, and this energy is then transferred into as heat in the resistors. Okay. And you can measure this energy with a voltmeter. So 9 volts. 9 volts means 9 joules per coulomb of charge. So let's make a note of that. Battery supplies battery supplies 9 joules of energy to every coulomb passing through. And a coulomb, I just remind you, 1 coulomb is just a bag of electrons. It's a bag of electrons. Okay, you should be familiar with this. Bag of electrons. And how many electrons in that bag? Does anyone know how many electrons in a coulomb? Or at least how can you calculate how many electrons in a coulomb? Can people hear me, by the way? 6.25 times 10 to the 18. Very good. Yes. Okay, then, lovely. 1 divided by elementary charge. Absolutely. That is correct. Yeah, it's 10 it's 1 point sorry, it's 6.25 times 10 to the 18 electrons. And let's just for fun imagine this number, because it's a really big number, but how big is this number? Well, imagine you Google Earth Imagine you go to Google Earth. And just for popcorn kernels. So this stuff. Copy image. Imagine you have popcorn kernels. And you wanted to take, imagine you had 6.25 times 10 to the 18 kernels. How much is that? Well, let's go to Google Earth and take how do I twist it? Okay, and take a snapshot. How much area can I cover? Any guesses? How much area can I cover with this popcorn? Yeah, we moved to Miro. Here's the Miro link. All of Europe, pretty much. You could cover all of UK, of course. You could cover Ireland, France, Spain, Portugal, like everything. Excluding Russia. Okay. You could cover all of this, excluding the Black Sea, of course. So you could cover all of this area with unpopped popcorn. To a depth of about 1.5 meters. Approx. 150 centimeters deep. This is how big this number is. Okay, I couldn't resist. Just to imagine. It's it's massive. The number of electrons in a coulomb is absolutely massive. The battery supplies 9 joules of energy to each coulomb passing through. Yeah, but you don't take you don't. Why would you care about the surface area of a popcorn kernel? No, you don't need the surface area. You need the volume. I calculated by volume. So you take the volume of a popcorn kernel, and you multiply it by 6.25 times 10 to the 18, and then you divide by the area, and that gives you the height, the depth of popcorn kernels that you can use. Okay, so if you take an ammeter, it measures the current. So what does the current tell you? Well, the current simply means how much how many coulombs pass per second. So this is just how many coulombs. So 0.3 coulombs pass every second. And that means the current 0.3 amps means 0.3 coulombs per second. 0.3 coulombs per second. And this 9 volts means 9 joules per coulomb. 9 joules per coulomb. Okay, lovely. I hope that makes sense. Then we have and some intuitive stuff about voltages. So let's pump this up to 24, and let's make this 10, 20, and 30. You know what? I actually want to replace them with light bulbs. Okay. Some more dramatic experience. Okay. And I'm gonna take this 10, 20, and 30. Okay. Well, first thing that you notice that which lamp is the brightest? Yeah, the one with the 30 ohm, light bulb is the brightest. What if you connect them in parallel? Which one would be the brightest if you connect them in parallel? So this is 30 ohms. This is 20 ohms, and this is 10 ohms. Okay, then says the first one, and the Ray people say it would be the same. So let's see. So if they are in series, so obviously they have. So this is 24 volts, and because 24 volts splits equally between the 3 light bulbs. So, well, splits between the 3 light bulbs, not equally, not in any case equally. So this can be 4 volts. This is 8 volts, and this is 12 volts. So they split in proportion. And obviously, because this is 12 volts, it means we lose more energy on this light bulb. Okay, every coulomb gains 24 joules in the battery. It loses 4 joules in the first bulb. It loses 8 joules in the second bulb, and it loses 12 joules in the third light bulb before coming back into the battery. So the electron, the coulomb, the 1 coulomb, it has 24 joules of energy. After leaving the first bulb, it has 20 joules of energy. Then it has 12 joules of energy, and after losing 12, it now has 0 joules of energy, and it comes back into the battery to get some more energy. So we have a cycle. the Coulomb moves anticlockwise. Now, if I connect them in parallel, an interesting thing happens. So I can't really see, so I'm going to reduce the voltage to, let's say 12. No, actually, let's make it 8. Okay, so you can clearly see that the 30 ohm light bulb is now the least bright. The 20 ohm is the middle one, and the 10 ohm is the brightest. Interesting. Well, because this is 8 volts, this is 8 volts, and this is 8 volts, and this is 8 volts. So every Coulomb still delivers, every Coulomb delivers 8 joules of energy. But because they have different resistance, there are going to be more coulombs passing, more current won't be passing through this one, but more coulombs will flow through the 10 ohm. The 10 ohm. Does that make sense? Because if you measure the current now, measure the current, it's 0.8, 0.4, and 0.27. Okay, so there's less current here, there's more current. Okay, 0.8, 0.4, and 0.27. 0.8, 0.8 amps, 0.4 amps, and 0.27 amps passing through. And of course here we have 1.4, 1.47, 1.47 amps. Okay, I hope that makes sense. Any questions? So we start with some resistor networks. We know that in series, resistance increases. In parallel, resistance decreases. So in series resistance, the total resistance is equal to resistance 1 plus resistance 2 plus resistance 3. And in parallel, the total resistance is equal to 1 over the total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3. For two resistors in parallel, you can use a simplified formula, because if you take 1 over R total equals 1 over R1 plus 1 over R2, You can simplify that, R1 plus R2 divided by R1, R2. So R total is equal to R1, R2 divided by R1 plus R2. This is a useful formula. It doesn't look very pretty for 3 resistors, so I wouldn't recommend it using it for 3 resistors, but for 2 resistors it looks very much easy. So we have a resistor network, and we need to work out the total resistance. Okay. Well, let's label the resistances first. So R1 is 1 ohm, R2 is 1 ohm, R3 is 10 ohm, R4 is 8 ohm, R5 and R6 are both 1 ohm. 1 ohm. Ula, you are asking a very good question. Now, this is very much a simplification. Okay. They don't physically have this much energy. The energy is the difference in energy. Okay. The coulombs have an additional so much of energy. But in fact, if you look at it, if you look, why do we have current? The picture is going to be quite different, because if you look at a wire, like let's take a wire with high resistance. So okay. So imagine I have a wire with high resistance. Yeah, so the difference between a current and a short circuit is whether the wires have sufficient resistance or not. So if the wires have a lot of resistance, there's not going to be a lot of current. And I can see that there's a current flowing through this wire. And if I take a voltmeter, I can see that there's a voltage across the wire. So if I look inside this wire, the wire is full of electrons. They're free electrons, because that's how metals work. Why does a current flow? Why does a current flow? Well, these electrons, and so this is a battery, so this is plus, this is minus. So it means that this part of the wire has more positive charge, and this has more negative charge, more like positively charged, negatively charged. And there's an electric field, or there's an electric field inside the conductor. There's an electric field that goes all the way around. But for simplification, we can just look at this section. There's an electric field inside the conductor, and it goes from plus to minus. And this electric field pushes the free electrons. Electric field pushes free electrons. So it's not the battery. The battery doesn't push them. They're being pushed by the electric field, which is produced by the battery. Does that answer your question? The electrons accelerate towards the positive terminal of the battery. So when I say they have zero energy, they don't. If that makes any sense. They don't, we can say they have 10 joules of energy here, but after the battery, if this is a 24-volt battery, they have 34 joules of energy. So the battery is just a difference. It's not actually zero. Let's say zero additional energy, if that makes any sense. So when I say they come to the battery, they now have 0 joules, they might as well leave the battery with 30 joules, go down to 26 joules, they go down to 18 joules, go down to 6 joules, and then go back to 30. So it's an arbitrary number. It's like gravitational potential energy. Gravitational potential energy depends on where you're measuring from. So yeah. Okay. So what I like to do with this is I can just find sections, or I like to straighten up the wire first. So I can straighten up the wire, and this is R1, and this is R3, sorry, R2. This is R4. This is R5. This is R6. And here I have R3. So you can see how these two are equivalent, right? Now, this is equivalent to that. So all I done is just straighten the wire out. Now I have R2, R4, and R5. So that's 1, 8, and 1. That's 1, 8, and 1. So that makes a total of 10. So it's equivalent to 1 ohm, 10 ohm, another 10 ohm, and then 1 ohm. But I know 10 and 10 in parallel, that's a total of 5 ohms. So this is equivalent to having 1, 5, and 1, which makes a total of 7 ohm. So the answer is 7 ohm. Our total is 7 ohm. Okay, do you understand how I did this question on a scale of 0 to 10? Thank you. All right, question 2. Now we're getting places. An infinite chain of resistors. But they are in series, so that's going to be easy. All right, they're all in series. So the total resistance is the resistance 1 plus resistance 2 plus resistance 3 plus etc. So that is 1 ohm plus 0.5 ohm plus 0.25 ohm plus etc. infinity times. What is that equal to? Does anyone know? Very good. 2 ohms. 2 ohms. Does anyone not know that it is 2 ohms? I'm happy to explain. Don't be shy. You can send me a direct message. So everybody knows why it is 2 ohms. Well, it's not. No, it's not. It's in the Bayesian problem. It's you have the squares. Okay. So this is, well, first and foremost, it's a geometric sequence. It's 1 plus 0.5 plus 0.25. It's a geometric sequence with r equals 0.5. And the sum to infinity of a geometric sequence, there's a formula, is the first term divided by 1 minus r. So that is, the first term is 1 divided by 1 minus r, 0.5, which makes it 1 divided by 0.5, which makes it 2. So the sum to infinity is 2 ohms. Does that explain, Julian? Yes. Another explanation is graphical, and I really like the graphical explanation. Imagine you have a square of side 1. So that means the area of the square. It's a 1 by 1 square, so the area is 1. Now, if you cut the square in half, this is 1/2, and this is 1/2. Now you cut the other half in 2, and this is a quarter, and this is another quarter. You cut this in half, and this 1/8, and this is another quarter. It's just 1/16, 1 on 32, 1 on 64, etc. But as you keep going, you're staying within this square. So you can say that 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus infinitely is 1. But because we have 1 plus a half plus then we have 2 ohms. So it's more like a mathematical question rather than a so the answer is 2 ohms. And if the question is what is the current is going to be 3 amps here. There's a joke. I don't know if it's a famous joke or not. So you have an infinite number of mathematicians walk into a bar, and the first one orders a pint of beer. The second one orders half a pint. The third one orders a quarter of a pint. And the bartender said, "Oh, I hate you guys," and just puts 2 pints of beer onto the tabletop. So yeah. Okay, let's talk about this one. So this is a parallel combination. It's infinitely many resistors, and it's 1, 2, 4, 8. So on one hand, as you add more and more resistors, you should have a drop in resistance. But then each consecutive resistor gets bigger, it gets more and more resistive. So maybe there's a limit. So let's have a look. And so 1 over our total is 1 over 1 plus 1 over 2 plus 1 on 4 plus 1 on 8 plus etc. Ah, it's the same thing, isn't it? 1 on 1. So that is 1 plus 0.5 plus 0.25 plus etc. to infinity, and that's equal to 2. So 1 over the total resistance is 2. So total resistance is 0.5 ohms. And the current here is going to be 12 amps. And out of 12 amps, we know that 6 amps will flow here. 6 amps because the resistance of this is 1. We have 3 amps and 1.5 amps, and this one is going to be 0.75 amps, etc. Okay. And if you add the currents as well, so 6 amps plus 3 amps plus 1.5 amps plus etc. infinity times, you should give an answer of 12. Let's see. So R is 0.5. The sum to infinity is the first term divided by 1 minus 0.5. So it's 6 divided by 0.5, which is 12 amps. Okay, so it works. 12 amps as well. All right. So a fun little question. Now we're getting to some interesting stuff. You have an infinite chain of resistors. It's a more complicated chain. And you need to find the total resistance between A and B. So resistance between A and B is a question mark. Okay, so basically, what we want to know is we're saying, well, if this is A and this is B, what is the single resistor? Let's call it RT. What is the single resistor that we can replace the whole system with? Yeah, nobody likes infinite resistors, right? It would cost infinity pounds, and it will take forever time to make, right? So it doesn't make any sense. The question is, what is the total resistance of this system? In other words, what is the single resistor that you can use to replace the whole system with? And we need to do it the following way. Well, as you can see that this chain is made of identical chains. So infinity and infinity plus 1 is the same thing, right? So adding one more chain link will not change the overall resistance. Okay? Because if it's infinity already, adding one more doesn't do anything. So what is adding one more? Well, adding one more literally means taking the infinity, taking the full resistance, and adding 3R here and a 4R here. Are we on the same page? How well do you understand what I've just did? On the scale 0 to 10, please. So what I've done is I replaced the whole system with a single resistor, which is RT. And because the chain is made of an infinite number of resistors, adding another 3 and another 4 will not change the total resistance. So an RT plus a 3 and a 4 will still be equivalent to RT. Oh, sorry. Very sorry. No, I messed up. I messed up real bad. You didn't see that. Okay. So this whole thing can be replaced with a single resistor. Adding another chain, another link on the left. So adding another 4 here, 4R, and a 3R here. I forgot that I can't add on the right. I can add on the left. Adding another 3 and another 4 here will not change the overall resistance. I can add another 4R, 4R, and a 3R, and the resistance will still be the same. Okay. Therefore, if I replace the whole chain with RT and put another 4R and 3R here, 3R, the resistance between, so let's call it CD, resistance CD would still be the same as the resistance between AB, which is the same as the RT, or just simply that. Resistance between C and D is exactly the same as R total. To those who were not 10s, does that make more sense? So the overall resistance is still RT. Yeah, you can't put at the right end, of course, because it's an infinite. You can't. So yeah, sorry. I've been yeah, working nonstop for probably 4 hours. Brain's not functioning properly. Okay, so RCD is RT. So now, what's the total resistance? So resistance between CD. Well, you can see that it has a combination of these two. So these two resistors in parallel. So resistance, we're going to use that formula. So R1, R2 divided by R1 plus R2. That's our total. So the resistance, the total resistance is going to be 3R, because that's in series, 3R plus 4R times RT, 4R times RT, divided by 4R plus RT. Ooh, that looks like an equation that we can solve. So let's multiply everything by 4R plus RT. And that makes it 4R plus RT, 4R plus RT, multiplied by RT equals 3R multiplied by 4 R plus RT plus 4R RT. So 4R RT plus RT squared equals 12R squared plus 3R RT plus 4R RT RT squared minus 3R RT minus 12R squared equals 0. This is a quadratic equation. I'm going to solve it by using the formula. So the unknown is RT. RT is the unknown, and it's a quadratic equation. So the discriminant is b squared minus 4ac, which is 3r squared minus 4 times 1 times c, some minus 12r squared. So that's 9r squared plus 48 r squared, which is 57 r squared. So r total is minus b, so 3r plus minus square root of 57 r divided by 2. So because of course it can't be negative, so the total resistance is 3 plus root 57 over 2r, which is approximately 3 plus root 57 divided by 2, 5.3, so roughly 5.27 r. That's the answer. In your assignment, you will have an easier question because you wouldn't have surds, but effectively it's the same thing. Okay. So you add another chain on the left, and yeah. You're familiar with, so problem 4, you're familiar with resistivity, and in the A-level course or equivalent course, if you're doing something else, you will learn about resistivity, and resistivity is the resistance per unit length well per times the area. Well, it's resistance per, it's the resistance per unit length per area. Sort of this is the idea. Resistivity. However, it is a resistance per unit length. There's another value. Resistance per unit length is simply the resistance per unit length, just like that. There's a question. How do you know that adding one more chain wouldn't affect the total? The total. Well, because there's infinity of them, and adding one more gives you an equivalent chain. No, if you have an infinitely long chain, adding one more to the left doesn't make it different. It's the same one. Same thing. If you have a sequence of 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, If you add another one, if it's infinitely long, if you add another one on the left, that doesn't change anything. Okay. If you start with one, add another one. If you start with one chain, so there's a question, can you say, can it tends to that answer? If we have one chain link, we find the resistance. The resistance is 7 R, of course, because 3 and 4 is 7. If we add another one and we find the resistance, it's going to be something else, but it's going to be closer to 5.227. Yeah, you can say adding more links, the answer will tend to our total. Actually worth checking that out, worth testing. Does it actually work? Okay, problem 4. Find the resistance between C and D if the resistance per unit length is RL. So resistance per unit length is another valuable thing. So if you were to I don't know, design a heater, an electric heater, you're not really interested in the resistivity. You're interested in the resistance per unit length because if you know the thickness of the wire, why would you calculate why would you need to use the thickness of the wire if it's much more convenient to so this is much more convenient in practical applications. More convenient in practical applications. Example, wire has 0.2 ohms per meter. How long does the wire need to be? Does the wire need to be for a 2,300 watt kettle? So if you are making the heating element out of this wire, how long does the wire need to be if you want to make a kettle? Well, you know that the voltage is in the mains is 230 volts. So the resistance is voltage divided by current. The voltage is 230 volts, and the current, well, current is power divided by voltage. So it's 230, so it's 10 amps. So that's 23 ohms. And then the length is going to be the resistance divided by the resistance per unit length, which is 23 ohms divided by 0.2, which is 115 meters. So you need 115 meters of wire. So you can see how this is much easier than you would have to use this cross-sectional area of the wire, right? So if you are a person who makes kettles, why would you need that information? You need this information, a resistance per unit length. Okay. Right, so find the resistance between C and D. Well, we assume that they're all connected. Okay. And, well, we can imagine a small resistance here small resistance here, a small resistance here, a small resistance here, a slightly bigger resistance here because it's longer. So the resistance is the resistance per unit length multiplied by the length of the wire. So if the radius of the circle is r, the radius of the circle is r, then the resistance of this one, the resistance of this wire is r RL, r RL, r RL, r RL. Now for this one, now this is a quarter of a circle. The whole circle is 2 pi r, the length of the whole circle. So divide by 4. So it's pi r over 2 RL. So pi r over 2 RL, pi r over 2 RL, and pi r over 2 RL. That's the length of these sections, and therefore, using this formula, resistance is R times L. Do I? Okay. Now, the resistance between C and D, so this is point C, this is point D. Let's rewrite it. So from C, there's this resistor, there's this resistor. Let's, for simplicity, let's call it, let's give them different names. Let's call this R1, R1, and this we'll call R2, R2, R2. So I'm going to redraw this. So this is going to be R2, R2. Then there's a link, then there's another R2, and another R2. And then to D. And then there's a link here, so there's R1 and another R1, and another R1 and another R1. Now, there's a problem here. There's a problem here because you can't break it down into convenient series and parallel links. Okay. However, you can look at the symmetry. Imagine you are an electron. You're an electron. You come from here, the top. You go to point C. You have a choice whether to go left or right. And then when you reach, no, sorry, what doesn't work like that. Doesn't work from the point of view of an individual electron. But it works. Imagine that these resistors weren't here at all. Imagine this was blank. It was not connected. And if you have 8 volts, if you have a potential of, say, 8 volts here, then by halfway through, you lose half of your energy. And here you have 0 volts. So the current comes in from here, 8 volts here, the potential is 8 volts, potential is 4 volts, the potential is 0 volts. Halfway through the wires, you always have 4 volts. 4 volts. But that means that the potential difference between these 2 points is 0. The potential difference between these 2 points is also 0. That means the current will not flow. So these resistors are actually pointless. They don't make any difference whatsoever. And let's show how that works on a real example. So imagine you have a battery and resistors 1, 2, 3, 4, 5, 6. Now the middle resistors are different, but they are identical. That's important. Let's make them 5. So this is 5, 5, 10, 10, 5, 5, 10, 10. Now I connect them. Okay, this is going to take forever. So I'm just going to simplify it. Okay. So what happens here? So if I take a voltmeter and let's make this 8 volts. So here, of course, the voltage is 8 volts. And across any pair of resistors is 8 volts. But if you take the voltage across any individual resistor, it's going to be 4 volts. Because it's 4 volts here and 4 volts here, the electrons have equal energy after leaving the first resistor. It doesn't matter which one, they still have equal energy. And if we measure the potential difference between these 2 points, it's going to be 0. And the voltage across these 2 points is going to be 0. So if we place a resistor here, the current in that resistor is going to be 0 because the potential difference across is 0. So this resistor doesn't change anything. It's like a nothing. Current doesn't go there. So if we delete it, it's still the same. Has no effect. More into that, we can replace it with a wire. And the wire will still have no current inside. Okay? Do you understand? Do you understand what's going on here? Current only flows if there's a potential difference. And if there's no potential difference, current will not flow. We can say that here is 12 volts plus 12 volts, plus 8 volts. Plus 8 volts. Here's 0 volts. This is 8 volts. This is the potential. 8 volts, 8 volts. This is 0 volts, 0 volts, 0 volts. So we have potential difference. There's a potential difference, and that's why current flows between the 2 points. Electrons move from low potential to high potential, or we can say positive charge goes from high potential to low potential. But halfway through, the potential is 4 volts. 4 volts. So the potential difference is 0 volts between these two. And here the potential difference is also 0 volts. So current will not flow. Does that make sense? Do you understand? Please let me know. Everybody's being very quiet. Okay. Yeah, when there's no voltage difference, the electrons don't flow there. However, I have to mention that if you, let's say this was 10, this is 10 ohms, the electrons would flow, but because as a result of them flowing, the potential difference would still be 0. Because they flow. Well, the potential difference, because the potential difference is current times voltage, or current times resistance. But if the resistance is 0, voltage is also 0. However, if I were to remove this wire, the voltage is not 0. So a wire will equalize the voltage, make it 0. So the current wants to flow, the current does flow, and as a result of the current flowing, the voltage changes. If you take a resistor, it's going to be a different value. So if there's a current, if a current does flow, it will change the distributions of voltages, and that's perfectly normal. Current will flow through a wire because the wire has 0 resistance. Because if you remove the wire, look, if you remove the wire here, so the voltage here is 0, right? And yet it looks like current is flowing. So let's remove that. Right. There's 0 current, there's 0 voltage here, and yet you see that current flows through the wire. But the wire has 0 resistance. And it does make sense. 0 times I is 0 volts. However, if you were to remove this wire, look what happens to the voltage. That doesn't make sense. Okay, that's a mistake. The voltage here is 8. Okay, so yeah, it's just it's the simulation is not correct in this particular reasoning. In reality, the voltmeter would show 8, not 0. And adding a wire changes that to 0. So if adding a wire changes it, that means current would flow through the wire. If adding the wire doesn't change the voltage, then the current would not flow through the wire. Okay. Hope that makes sense. If I add another wire like this, still some current flows, but yeah. Also, in wires, there's always a current. There's always a small resistance in wires if it's not a superconductor. Then, yeah. So here, these resistors, because of the symmetry of the network, these resistors are pointless. And therefore, can remove them. These resistors are pointless. So the total resistance is equal to 1 over 2R2 plus 1 over 2R1, because the resistance is 2R2, 2R1, and 2R2, plus 1 over 2R2. So 1 over R total is that. That makes it 2R1, R2, and that is R1 plus R2 plus R1, which is 2R1 plus R2 divided by 2R1, R2. So R total is 2R1, R2 divided by 2R1 plus R2, which is 2 times R1. R1 is RL, RL multiplied by pi R over 2 RL divided by 2 times RL plus pi R over 2 RL. Okay, so we have RL cancels, one of the RLs cancel, and we have RL, so small r cancels. Oh, no, that's not possible. So one of the small r's cancel. So we have 2 cancels, pi r divided by 2 plus pi over 2. Yes, let's make it slightly prettier. So that's 2 pi r divided by pi plus 4 RL, and that's the answer. Okay, not a particularly pretty answer, but it works. Okay. Now then, the following 3 questions, you need to use Kirchhoff's laws. So this is an analysis task network. Yeah, well, you use Kirchhoff's laws, Kirchhoff's first law and Kirchhoff's second law. So how do you do this? Well, first of all, you assume the direction of current. So here the current flows, this is the plus, this is minus, so current will flow in that direction. Now here the current will split. I assume that some of it goes here and some of it goes here. Now here the current will split again. Now the current here won't go that way, and this current will split again. Well, which way does current go through R3? Well, we don't know. My guess that it won't go up. It might as well go down. But I don't care. I say it's going to go up. Okay. This is the first step. First, draw currents. Draw current. Now I'm going to add pluses to each. So step 2, add plus and minus on each component. How does that work? Well, for high potential to low potential, current always flows from high potential to low potential. So in the resistor, if I go from, the current goes from right to left, this is plus and minus. For R3, current flows from plus to minus, so high potential to low potential, plus, minus, plus, minus. Okay. For the battery itself is obvious. Plus is plus, minus is minus. So plus is high potential, minus low potential. So let's say this potential here is 12 volts and the potential here is 0 volts. That means the potential here is 12 volts. Along the wire, the potential is always the same. It's like the potential energy of this. And here, let's say it loses 3, so it's going to be 9 volts. So the high potential, low potential, plus, minus. It doesn't have to be negative potential. It could still be plus. It's just not. It's lower. Okay. And add plus and minus on each component. 3. Okay, draw currents and label them. Okay, I'm going to call this I0 because, yeah, I'm going to call this I2. I'm going to call this I1 because it's R1, I1. Makes perfect sense. Now for this one, I can call it I3, but I already know that I3 plus I2 makes I1. So I3 is actually I1 minus I2. So right here, I can write I1 minus I2. Yeah, does that make sense? Because I2 plus this makes I1, because they join together to make I1. Okay, I4. Well, if this is I0, and this is I2, I can call this I0 minus I2, right? Because if I take away I2 from I0, and this is I0 minus I2 still. So this one is I2, I0. Oh, okay. Actually, you know what? This is I0 and this is I1. So this is I0 minus I1. Lovely. So I've labeled the currents. 3, choose a loop and go round the loop. Okay. So Kirchhoff's second law says that if you have several components, and E1, sorry, EMF1, EMF2, V1, V2, V3, V4, V5. You are taught in school that the Kirchhoff's second law, Kirchhoff second law, goes like this, that the total EMF is equal to V1 plus V2 plus V3 plus V4 plus V5. Okay. The particular side of the components should place the eyes. No, there's no particular side. It's just along through the wire. Through the wire, the current remains constant. But I mean, look, these batteries work against each other. You don't even know which way the current is in this network. So this one is plus minus, and this is minus plus. So they will push against each other. They will work against each other. The total EMF total is EMF2 minus EMF1. But what if you have a even more complicated network? There's going to be a problem. So what we say when we're talking about electrodynamics, I wouldn't call this electrodynamics. It's just too far-fetched. We go around this circuit. So, choose a loop and go around the loop. If you go from plus to minus, to minus, it's going to be negative because you're losing energy. If you're going from minus to plus, it's going to be positive. Let's see how that works. You're going around the loop, adding voltages. So I choose a loop. Let's highlight the loop. Let's go to green. Let's do a simple one. So what do I have here? I have the EMF. And I choose to go through the loop anti-clockwise. I choose to go through the loop this way. So I go through minus to plus. So minus to plus is positive. So it's plus EMF. And then I meet a component. The first component I meet is R4. So I4 is from plus to minus. So it's going to be negative. So minus V4. Reach, and that's equal to 0. So I've went around the loop and I've added all the voltages, and they should add up to 0. That's Kirchhoff's second law. Now V4, I know that V4 is IR. I use the Ohm's law. V4 is I4 multiplied by R4. So EMF minus I, which is I0 minus I1 multiplied by R4 is 0. And that's my first equation that I'm going to use. First equation. Now I choose another loop. Let's take another green loop, and let's go this way. Okay, so that's going to be plus EMF minus I2 R2 minus I1 R1 equals 0. In other words, EMF, well, yeah, that's it. That's the second equation. Okay, how many do I need? I have three unknowns, I0, I1, and I2. So I'm now gonna use R3 as well. So I'm gonna go around the loop. I'm gonna make another loop, and let's just make this way. And so that's gonna be plus EMF minus I3 R3 minus I1 R1 equals 0. And that's my third equation. So I should be fine. 3 equations and 3 unknowns. It should be fine. And well, I3. Oh, sorry, I can't use I3 because I don't have I3. Instead of I3, I have what? Instead of I3, I have I1 minus I2. So I'm going to rewrite this EMF minus I1 minus I2, R3 minus I1 R1 equals 0. And that's my third equation. All right, so let's see what we can do here. Okay, let's use the values for the resistances and the EMFs. So I'm going to rewrite this. 2.8 minus I0 minus R4 is 7. Minus 7 I0 minus plus 7 I1 is 0. From here it goes 2.8 minus I2. R2 is 1 minus I2 minus I1, which is 1.25. 1.25 I1 was 0. And the third equation, so EMF minus R3, 3 ohm, minus 3 I1 plus 3 I2 minus R1, 1.25 I1 equals 0. And this is 2.8, 2.8. As you can see, this is simultaneous equations with 3 unknowns. I don't have time to finish it, but it's doable. You can use, yeah. So we'll finish it in 2 weeks' time. And this is, I'll go through it in more detail. All right. Just a quick show of hands. How did I lose you? Do you understand? How well do you understand this method? How well do you understand this method? Did I lose you? No, I didn't. Or no, you don't understand. So loss, I mostly get it. Okay. Well, have a go at the problems, look at the examples, and we'll carry on in 2 weeks' time. Yeah, hopefully it will make more sense then. All right. See you then. Enjoy your weekend.